So, object-oriented programming. So, if you have started with your first Python exercises, you will probably have used objects in some form or another, because everything in Python is an object. And an object is a collection of data and associated methods. So it's kind of, you group them together. So for example, a string is an object. Object stores characters, a set of characters, and a set of methods to operate on those characters. And together that forms a string object. And there is also the dictionaries, the lists that we talked about. All of these are objects. Data types, of course, but they are also objects with methods, so that you can call on them, you can sort them, you can do a lot of things by sending them operations. But they store some data and they have associated methods on them. So what we're going to do today is to understand the fundamental concept of object-oriented programming. This notebook here contains a lot of stuff that you probably will not need, but if you're interested and want to kind of dig some deeper, you can go into this and see, because it contains most of the things that are important for object-oriented programming. You will learn how to create classes and objects yourself, because that is also something you can do in Python. Just like we did with functions, we can create our own data types and objects. We also learn something about how to encapsulate data, build composite objects, so objects that contain other objects, and also apply something called polymorphism to treat a set of objects in the same way. So different objects, but you operate them in the same way. So, what is object-oriented programming? I already gave you an overview here that is a combination that you operate on objects rather than functions. And the basic idea is to combine data and functions together in an object. Usually objects represent things like nouns. So it could be a point, circle, string, bank account, something like that is a noun. And you interact with this object by sending messages or calling methods. You already did that in the string we have this split function, and that is a method that you call on the string to do something. And those methods are also known as the verbs of the objects. Then you also have something called attributes that are describe the objects, some of the characteristics of the objects. It could be, for example, a point can have a position, x, y coordinates. And then the concept of a class, that is a blueprint, how your data type or object will behave and what attributes it should have. So it's a blueprint. Remember that all the time. A class is a blueprint. It's not the actual object, but it's a description of how an object should look and how it should work. So the benefits of object-oriented programming, it's code reusability. You can write once and then you can use it many times. Modularity is easy to maintain and debug because you conceptually know how the objects are related to each other, and then you know how it works. Abstraction, that you hide complex behavior inside the objects. And then you also hide implementation details. Encapsulation is that you can provide data types to your users of your module that they don't have to know the inside of it. You protect the internal attributes and variables for the user of the object. So you then later are free to change the behavior of the object in a different way. Inheritance, that is that if you have existing classes, you can derive new classes from other classes. So you can, for example, you can have a point base class, and then you have a circle that inherits the basic characteristic of a point, but adds a radius to it, for example. Polymorphism, if you have classes that are derived from point, you can treat all point-derived classes in the same way because they have the same methods. So you can, and Python knows which method to call on the correct object automatically. So just kind of see the difference between function-based programming and object-oriented programming. So I will create a module here in Python that is a function-based. So in function-based programming, you have functions that operate on data. And then you have a data type that you pass along to your functions. The functions do some operation and on that data. So let's see here. So for example, this is a module for handling points, moving points, printing points, and so on. So the base data we are going to use here is a list of x and y coordinates. So you create a point by calling the createPoint method with x and y methods. It returns you a list of x and y. You don't really have to know that it is a list, but in this implementation it's a list. So you hide the implementation inside of functions. Then you have movePoint. The first argument to the method is, of course, what point should I modify? Yeah, it's the point data here, and that is a list, so I can update the data structure here. I can zero the point and update the data structure coming in here. And because a list, that works, because you can modify the contents of the list inside a function. We have a set point to change the coordinate, print point to print the point, and then you have a distance from origin, for example, how long is it from 0, 0? Some methods here. And then I just kind of want to define those functions. This. So here you can see that I create a point here. I don't have to know what the variable p contains, because now I have a set of methods to work with those. So you can see here that I create a point, I print a point, I can move a point, I can set the point, and do like this. So this is a function-oriented program, and you can actually have a really complicated data structure that is only data that you pass along to the functions, and the functions work on that data, and the user of this library doesn't really have to know that it is a list. It could be something else. But you work on it by calling functions, and the first parameter usually is the data structure you're working on. So the problem with the function-based approach is that you don't have any data protection. So the user can go into your the point structure, and modify it however he or she wants. The functionality of operating on points is spread out over several functions. There is also confusion about the parameters. For example, you can have dx point dx, for example. There is no type checking. That can be added, I would say, but it's also difficult to extend, because you have to modify, if you want to modify the data structure, you probably have to modify the functions as well. And also you add a lot of function names into the global scope. So by using object-oriented programming instead, we kind of solve this problem by lumping these things together, data and functions, into a single object instead, which contains the data but also has method associated with it. So, as I said before, a class is a blueprint. It's kind of a template. So it's like my colleague at Lunar, he always said that you have a cookie cutter. So when you do pepparkakor in Christmas, you have a shape, and you can use that multiple times to create multiple pepparkakor. And the same thing here. A class is a cookie cutter. So you can use the class to create multiple objects. And the class also defines which attributes goes into the class or to the objects, and which methods are operating on the object. Then we have the object instance, and that is the actual concrete object stored in memory in your computer. So a string is a typical object. When you create a string, it's located in memory and it's there. And also each object has its own unique attributes. So every time you create a new object, it has its own x and y coordinates if it's a point. If you change that point, it will not change the other point. And you can create multiple objects from the same class. So here are some real-world examples. For example, a car blueprint. You can have attributes: color, model, year, mileage, methods: start, stop, accelerate, brake. So here you can see what an object is. So a car has some attributes and some things that you can do with it. And then you can create multiple cars. So my car color is red. It's a Toyota. It's a 2023. And then you have your car. It's a blue car. It's a Honda. And then a rental car is a Ford. So you can see you have 3 objects, and they are independent from each other, but they share the same methods. So they're all cars. They can all be started. That's the main idea. So here, another example is planets. You can have a planet class where you can create Mars, Jupiter, and Earth. They're all planets, and they can have all their own unique attributes. So, how do we define a class in Python? So, of course, there is a keyword called class, and it's similar to defining a new function. So you class name, you give it a name, colon. And then you define a special function called init. And this function or method is called when you create a new object. So that is always called. And what you have to provide there is the attributes that define the class. And here also comes a very special parameter called self. Because it's a template, we don't know when we create a new object the actual storage location in memory. So the self variable represents the actual object when it has been created. So self is a kind of reference to somewhere in memory. So the parameter here, self.attribute, here I connect an attribute and assign a value to that. But the self is actually the actual object when you create it. So every time you create a new object, init is called with a different self variable. So it refers to the actual memory location in your computer. And self is, for all the methods that are operating on your object, you need to have the self as the first parameter, always. You will never call your method with a self parameter that is handled by Python automatically. So reference to the current instance. And sometimes if you come from other languages, it can also be called this. So let's create our first class. So we create a point. So we have init. And a point needs to have some x and y coordinates, of course. So what we do then is we just assign self.x equals to 0, self.y equals to 0. So until we do this, the object will not have any attributes. So you need to actually assign attributes to the in the init for them to be added to the object. We can skip that one, but we will define it. So I already explained this with self. So self is the reference to the instance object. You create a new object. It's just like when you do a string and all that, you create it in the same way. Object name equals to and your class name. So in the point case, you have p equals to point. You need to have the parentheses here. And in that moment, init is called. So every time you create a new object, init is called. Init adds the attributes, the object is finished. So it's kind of, init is the object factory to create the actual object itself. So here you can see here that I have point with ID. That is the one that printed out the ID of the objects just to see that they are different. And then you have p equals to point, q equals to point. So you can see here that every time we create, you get a new object, and it's located in different parts of the memory. And you can query this here also with ID function. So each object has its own unique ID. Also, when you have your object created, you can access the attribute by doing the object dot and the attribute. So in this case here, you can see here that all initialized objects have x and y 0 because you did that in the init function. You can also assign p.x equal to something, and then that is changed in the object. The problem with this approach here, that we have attach attribute directly and let the users change the attributes directly, is a bit dangerous because the object itself doesn't know if something has changed or if it's something has to be done when you assign a certain attribute. And the idea of that is the next concept we're going to look is the encapsulation and data protection part. So that means that you are hiding the internal attributes from the user and controlling the access to internal data. In our previous example here, we just added some variables. Those variables can be changed by the user, and we don't really have control. So for data integrity purpose, to prevent invalid values, so if you have a, let's see, finite element model that has a thickness parameter, you don't want the thickness to be minus or negative, and you want the thickness to perhaps have a maximum value. When the user sets my beam object b.t equals to -1, Python happily assigns that to -1, and the beam object doesn't know anything about that. So to handle that, we need to kind of encapsulate the assignment of attributes in a more. So for example, you can see here that I have a point here, and I can assign it whatever. I can assign it a string, I can assign it a list. There's no checking at all. It just works. Sometimes that's okay, but for many cases when you're a more complex program, you need to control what happens with your object. What you can do in Python is you can set some attributes to be private. And what you do then is you add 2 underscores to your variable name. Then they are not accessible from outside. So if you modify a point, we can see here that instead of setting self.x, we set self__x equals to x, self_y equals to y. And then we add a get coordinates here to return those values here. So if we define this here again, we will try here, we create a point. All those 3 here will work perfectly fine. So no problem. And we can get our coordinates here. But what happens if we try to access them as attributes on the thing here? So for example here, I added some exception handling here because when you try to access, you get an attribute error. So let's run this here. You can't access the internal attribute. If I try to do it outside here, you can see that I get a. No, sorry. Because there is no x. And also, if you try to access the p__x here, you will also have a problem. Because when you do __x, Python does some mangling of that name and hides it, so you can't actually access it. And that is a feature to be able to hide things internally. There is actually a way of doing it, but this is not something you should do. So actually, what it does, it changes the name to point, __x. So don't do this in real code, but you can actually access, because in Python everything is a dictionary. Even the object itself is a dictionary with all its attributes and methods built in. So Nothing is really hidden, but don't try it. So what we can do is, instead of letting the users access the attributes directly, we can build in methods for accessing the data. So for example, we can add an x and y function that returns the x value, and we can have a set function to set x and y. And then we can use it like this. So, sorry, you have, I need also have to, something like that. It comes later here. Should. And here we set the values here. So then we have some methods here, and in those methods you can do checks. You can check if x is greater than something, don't cap it at that value, for example. And here is another example. Here we have, we instead of using x to set things, we use x to return, and then we have set x to set the value, and so on. And now we have a class that has access. You can access everything internally, but you don't have access to the actual attribute inside a class. But you can get the values, you can set the values. And what that means is that if I want to store the variables in a database instead, I can change my class to store them in a database externally, for example, somewhere on the internet, but the user doesn't have to change his code, because the internal implementation can change and the usage of the class can stay the same. And that's one of the points of object orientation, that you can encapsulate things that you want to be able to change somewhere, but the user of that module or class can still use the same syntax and same methods. But in Python, of course, there is a so this here doesn't look very Pythonic. So if you want to do it the Pythonic way, you would like to. It's very nice when you can access the attributes just like p.x. So is there a way that we can do this and still have encapsulation? And of course there is in Python. So here you can see here that this is the without properties. Then you have a set method, a get method. And if you use the concept of properties in Python, you can use the normal attribute syntax, but still have a way of controlling how the variables are set, the ranges and everything. So how do you do this? Yeah, the first example here, we have our point class again, and we can, at the end here, you can see here that we can do this. We can add x equals the property, and what that tells Python is create a property that you can access like an attribute, and when a user tries to read it, call getX. If it tries to assign it, call setX. And now we can use this class just like the first example I showed you, where we just have the attributes. We didn't have any methods for accessing and setting everything. So you can see here, it calls the methods here because I have a lot of print statements here. You can see what it does. So if you x equals 42, you can see here that it setting x to 42, setting y, getting x value. And every time you have this print set, you can also add if statements to check the values of the incoming x and y values. It's a very powerful concept. I'm not forcing you to use it, but it's and that also means that we can start implementing classes in a very simple way, like using your attributes directly without using private things. And then if you want to make sure that you have control, you can add properties afterwards to these attributes that you want to protect. You add underscores to those that you want to protect. You add a property down in the class, and then you have the same interface but with the control. There is also another way of doing it. It's more you don't have to explicitly set up the properties. You can do it directly when you define your methods. And in this case, we have this property here. So this is a function x that returns the internal variable. I just add at property before the function, and now I can use x like a property. So for returning the value, but if I want to set it, I can add x setter on x here, and then you define a variable method called with self value, and here you do self underscore x is the value here, and that creates a write property as well. And then you don't have to do anymore. That's all. So now I can use so let's do this here again. I define point again. Then I do this. It's the same class again, but now I define the properties directly on the method by using this decorator method. And decorators are special meta programming function in Python, all beginning with an @ sign. And they modify the code automatically and generate the needed code for implementing the methods. Skip that one here. Discussed. Yes, so there are some special instance methods, and we already talked about the init function that is called when an object is created. There are some other methods that you can use. There is a method called str, which you can use to print objects or create a readable representation of an object. So for example, if you create your own object and you try to print it, you can see here that this already had a print statement, which is not so good. Yeah. If you don't have if you create your own points, if you try to print them with a print statement, you will get something like this. And this is kind of if Python doesn't know what an object is, and because this is an object you created, it doesn't know how to print it. And there is a print implementation so all objects in Python inherit from something called an object, the base object that is built into Python, and it has a print function. And if it doesn't know anything, it prints out all it knows. And in this case, it's part of the main structure, and then it's an object located at some memory location. But we can use a special instance method to access or create something that looks nice. And that method is called __str___. And that is called every time you call a str function or you call a print function. And then Python goes to calls that method and gets back a string representing that object. So what we do here, we just return a nice x and y point, x and y string. And if we run this here, you can see now it prints nicely a point. Yeah, so as I said before, classes are data types which you define. And they work just like any data types in Python. So if you have a list, you can, of course, add your own point. So in this case, I create a point instance and append it to a list. And I create random numbers here for the x and y coordinates. And I can, same thing, I can do it in this way as well. And I can loop over and print them. Because now we added an str method. So when we print the points, we get a nice representation of the points in our list here as well. And the same rules applies for points with this variable that is a reference to a location in its memory. And if you do this kind of replacement of what things point to, it works just like other Python objects. So in this case, P2 and P3 points to P0, and you can see that they point to the same memory locations as P0 and P1. Next, we will look at, so now we have looked at kind of the basic how to create a class that it inherits from the Python base object, but you never see that. But now you want to build upon your existing code. So the point is a bit boring, so we want to build a circle class and a rectangle class. And what you can do is you can use inheritance to reuse some of the parts in your classes. So here the basic syntax is that you have a parent class here. It doesn't have any, if it's empty here, it's inherited from the Python base class. But you can put a parenthesis here and tell Python, this new class inherits from my other class. And also, just those are curious by what false is. That is the most meaningless statement in Python. It just does nothing. And the problem is that you can't define a function without a code block. So if you want to create an empty function declaration in Python, you do a define function and you put a pause. Then you have a function that is empty and you can have it in the code. But if you just do a function colon, you need to put something in the code block. And pause is that statement that you can use. So in this case, I have two useless classes here that don't have any implementation, but they have a class relationship. They are related to each other. So the benefits of inheritance is that you can reuse code. You don't have to repeat common functionality. You can create a natural relationship between things. And also you can, one of the perhaps most important part is you can treat related objects in the same way. For example, you can loop over a set of geometric shapes. You can call a method on them to draw themselves, and they will each call the corresponding draw function for a circle, rectangle, and point, and so on. So for example, example here is a vehicle that is kind of the generic class, and then you have a car that inherits its base functionality from the vehicle, motorcycle inherits also from the vehicle, and truck and so on. And then you specialize the classes here, but they still have some things like for example, the license plate or the license plate number could be in the vehicle class, and then all the other one inherits that attribute from the vehicle class. So for our own things here, we will define a circle, and what is different from a point is that the circle also has a radius. So we have to again create an init function here that is a bit different from the point. We still need x and y points for the position, but we add another attribute called r. And if you have a derived class like circle, we need to be able to call the init of the base class as well before we continue, because otherwise the base class attributes are never initialized. So what we do then is we call a special function called super function, which gives you the base class. So it returns you the base class object, and then you can call init on that object, and then you pass along x and y. So what that actually does is calls the point init and initialize the point attributes. And then we add our own, so we need to add a self.r. Okay, we should have called it self like this. And we initialize that attribute inside here. Of course, now we know how to use properties. We define our properties here. And we also add some other convenience methods to our circles. For example, it could be nice to calculate the area. So we add an area method. We add a circumference method, copy from another circle. And then we also have to update the string function. If we don't add a string instance method, it will print a point. So because there is no other print statement, Python will go to the next base class, and oh, there's a string here, and then I use that, and then it will print the point. So we need to update that as well. So now we can use our inherited classes. We can create a point, we can create a circle. You can see here we can use them basically in the same way. Our circle now has the R property. It also has an area property. And you can see here, area here is actually read-only property. So you can't set the area because it doesn't know what we do to set an area, but you can actually return the area by just like an attribute variable. So in this case here, you can see that I'm using c.area, which is not a function, it's an attribute or property that returns the area. It will call the area method. Same thing with circumference. And you can see here also that the point included a move method to move it, and that is now also included in the circle. So the circle can also move. So let's run this here. So that is the way you can inherit it. So you can create new objects from an existing one. I didn't have to rewrite any code. I used all the code from the point and reused that in the circle. The final part here, we'll look at also the object orientation, the inheritance. Today is the recommendation is to create shallow hierarchies. Don't overdo the relationship hierarchies. It's better to use something called composition, that you have, you create new objects from objects. So inheritance, that is usually, you can say, it is a relationship, it is a relation. So circle is a point, then there's a clear relationship. Composition is has a. So a line has 2 points, for example. A car has an engine. A rectangle has 4 points. That is a composition. If you describe objects like that, you know that, okay, this is a composition object. It's not a relationship. Yeah, so when to use composition? When things are made of other objects, it's of course better to use the composition. And also when you need some more flexibility, you want to be able to change the objects a bit more flexible, then composition is also to use. There is a flexibility, loose coupling. You can have objects that are developed independently, connected together to a new object. With relationship, you have to be clear about the object inheritance graph and how they are really not very tightly coupled. So let's just do the final class here, the line. And a line consists of 2 points, but the points are not, so the line does not inherit from the points. It actually is it's an own object, but it owns 2 points, and that creates the line. So we use our points here, and we set our attributes internally here to P0 and P1. We have 2 properties P0, P1 that we can assign. We have a property called length to be able to calculate the length between the points, midpoint and so on, move. And you can see here that when we move both the internal points at the same time. We have a new str. But there is no inheritance here. So you can see that the line is standalone. It only inherits from the object. Yes? Yep. How do you mean? So if you, in this case, you can set the properties to something else, another thing other than point, if you want. But you can't build in, I don't have time to cover all that, but you can actually do set the type of the variables coming into the different methods. And then Python checks that it's correct type, but it's not done here. But one thing to protect you from the types, you can only have, for example, read-only properties. Then you can't overwrite the internal objects. So in this case, I have a P0 setter. And that can set to you can set that to anything and it will overwrite the internal with that object. But if you have only the property, you can only read the internal object. You can't change it. So that is one way of enforcing the types. In this here, I have defined the line to be very flexible, that you can assign new other point instances to the, but there is no type checking here. That's the kind of Python, the big dilemma in Python. It's very flexible, but it's also the problem you have that you can also do things that it's not checked. But the later version of Python has this, that you can do something called type annotation, and then you can, for example, in this part here where you set the point, you can tell it that actually you can do colon point here to enforce it. So you can't use another data type to assign here. And now you can see here we can do this. We can create a line, and then we have internal properties P0 and P1, which we can assign X, Y, and XZ to. So we reuse our class point, but create a new object by doing a composition. Let's see. So here is also what I told here. You can remove the setters here to make sure that you only can you can't reassign objects. Let's see, I can redefine this one here. Okay, sorry, it's the right way around. So you can disable this functionality here by making it only have read-only properties, not have the setters. Yeah, perfect. Yeah, finally, before we go to have a break here, polymorphism. One interface, many forms. So that means that if you have a class hierarchy of many different classes that are inherited from a base class that you have defined, when calling the method on the base class, Python will figure out, okay, this is a circle, so I should call the circle method of the str, for example. And for example, here I have a shapes list where I just fill that list with a lot of different classes, also objects, lines, numbers, and so on. And what I actually can do is I can print these all in the same loop. And that is because all of these, all of the data types in Python are objects. And they all have an str method. So you can all print them. And you can see here that when I print, yeah, it prints out everything here. The strange thing is, even a floating point number is an object. So how does it have a str method? And it actually has. So you can actually do this. Print 42 dot str. So even the floating number is an object which has methods. So it prints out 42, of course. So when you call str method on the floating point, what actually happens is it calls the str method to get a string back. So yeah. And also you can do geometric shapes here, so point, circle. Because everybody has a move, you can loop over the geometric shapes and call move on all the objects. And that will figure out which move object to call. Also, if you have them as a graphical library, you can have a draw method on every class that has its own implementation, and when you loop over them, it calls the correct draw method. So that was what I wanted to do. Where is my presentation record? Yeah, let's have a coffee break. Switch to Matplotlib. So this chapter will be a short overview of our Matplotlib, which is the plotting library that is kind of associated with NumPy. It's very similar to how and it's modeled on the how you plot in MATLAB. It's probably why it's called Matplotlib. So the nice thing with Matplotlib, it integrates with several of built-in or external modules that you will use. So you can use NumPy, you can use SciPy. Pandas is a special module for handling table-based data, and it interfaces with that as well. You can use it in Jupyter, which is the notebook interface. You can use it for Python directly. Basically, anything that can take things that are indexable can be plotted by using Matplotlib. So with Matplotlib, you can create simple plots, but also for really advanced plot that you can use for scientific publications. You can configure almost any aspect of the plotting down to the minute details. And Matplotlib also, you can do, what we will introduce in this course is plotting on the screen, but you can export everything to any file format you need. So from vector formats to PDFs to PNGs to JPEGs, everything is kind of supported by Matplotlib. I will skip that bit here. So how do you use it? So as with NumPy, there is a standard way of interfacing with Matplotlib. And so usually you do it in this order. You import NumPy. And what the interface, submodule we use for Matplotlib is the PyPlot module. And PyPlot provides a lot of high-level plotting routines that are useful for in this course and for normal scientific work. There is also a low-level matplot functionality that is available directly with the Matplotlib library module. We are not going to focus too much on that. We are going to focus on the high-level PyPlot interface. If you are using Jupyter notebooks, you can add Matplotlib inline here. Then you tell Matplotlib, okay, I'm running in a notebook. I should produce the plots without a window directly in line with the code. Then I some sets. So then you can print some versions here if you are really into this. And yeah. Oh, then this part here I have added this. If you want to do really nice consistent plots, you can define your style, and you can see here you can put a lot of your own parameter and configure them in a single variable, publication style. Then you know every time you plot something, you will get the same style. The architecture of MATLAB is that there is a backend for different kinds of output. So for example, if you want to plot on screen, there is an AG backend, there is a Qt backend, there is a lot of backend. There is also backends for plotting to files, plotting to vector files, and so on. And then there is the artist layer, which is where the base level drawing functions are. And those we are not going to use here. But you know that there is, and that basically means that you create the plotting from scratch. You don't have any help with anything. And there is the PyPlot MATLAB type style interface for quick plotting. And that is what we're going to use here. We're also going to use the object-oriented interface of that. That's why I introduced you to the objects now, so you know what to do. So, plotting. So what we are going to do is plot some X and Y series. And to start with that in Matplotlib, you create two objects, a figure and an axis. And the axis is the actual object that you are seeing inside a figure. So figure is just your outside frame, and the axis is where you plot. And in this case here, you call plot subplots, and then you give figure size 8 by 6. That is kind of just a relative size. And then you do plot, axis plot. So you told the axis, I want to plot my X and Y series. And then you set you call methods on the axis object to set the X label, Y label, or title of the plot. And now you can see here that you get a descriptive plot from that. Because we have inline, it's shown directly here on inside the Jupyter Notebook. And then I will skip this one here. So if you want to plot scientific data with NumPy arrays, that's actually really no problem. But if you want to plot functions, for example, I talked a little bit about that with NumPy. The MP linspace function is the function to use with plotting functions. So, for example, you create an X series here, and you create 50 points, and then you call Y equals to MP sin of X. Then you get a Y series, and now we have two series that we can plot. So here you can see the data here. And here is a really long version of how you can create a plot. So you create always the figure, the axis object, subplots, and the figure size. And then you create axis plot, that is a basic plot function. You give it a series, and here you can give it a color and the line. Or you can also set the line width, you can set the label. Alpha is the transparency level. You can set X and Y labels. You can set the title again, a grid, how transparent the grid should be, a legend, and then you can add some other lines inside a plot. You can limit the plot, xlim, so the 0 to 2 pi, y limit -2 to 1.2, and you can add ticks as well. And then plot type layout will look at all the plotting and make sure that you make it adapt to the space that you have. So here you can see that I have added some lines, and there is a legend here. And also I changed the line width here for this one here. You can change line styles here, so that you can use that by using some strings here: red, green, blue, C for cyan, and magenta and yellow. You can add markers by adding red O, for example, then you have red markers. And you can have line styles by adding dash. I think it's very similar to what you do in MATLAB. So here you have red markers. So O is a ring. And here you have black ring markers and a solid line, single dash. We plot this one here. You can see I have a first dotted line without any dashes. And then you have dashes and markers. And now you can see that this will be two figures in this case, because I call subplots twice, then I get two figures here as well. You can specify the parameters explicitly here in the call to plot as well, and do it later here as well. And then you can combine multiple figures in a single plot. In this case here, I have X is the same, and I have two Y series, just sin cos, so very simple. So this is my data. And then I can do, I create a figure object and an axis object, and then I can do plot multiple times. That will create multiple plots. And then I can add Y1, Y2, and then I plot it here. And now you have two series in the same plot. You can also create multiple plots. So in this case here, then I do subplots here, 2 by 1. So this is the rows and columns of your plotting where you want to combine the plots in. Then you get two axis objects. And then I call plot on these two objects, just like normally. And then you have another example here, which is 1 row, 2 columns. So this was what 2 rows and 1 column, and this is 1 column, 2 rows. So this is 2 rows, 2 columns. So this is how you can combine plots in a single plot. And then I will leave these other here. There's also some examples here of other plots you can do. When you want to do some plotting with Matplotlib, my recommendation is to go to the Matplotlib page. There is a gallery, and there is we can do that. There is examples here. And then you just, if you know what you want to plot, you just browse here, find the plot you want to do. Let's see if I can do. Then you click, and then you get the code. So don't try to read documentation too much. Go to the examples, look what you want, and then you go into here, and then you get an example how you can plot. So this is really useful. I just want to give you the highlights how you access the objects in Matplotlib to do the plotting. And the notebook contains, we can show some of the things here you can do. You can do histograms, scatter plots, bar charts, contour plots, which is kind of something we are going to use in this course. The nice thing is that you don't have to learn too much about Matplotlib because CALFEM will use Matplotlib to plot. So there are plotting functions that will do this for you. So, but what you want to do perhaps is add some finishing details to this as well. And you can use 3D as well. So it's a very powerful toolkit. So next, let's do some CALFEM. I had to switch to white background because some of the images were not showing on a black background here, but I hope we can read. So I'm just going to be a brief introduction how you use CALFEM for Python and do some examples how it's a bit different from the MATLAB version, but not very much. Yeah, so what is CALFEM? It's a clean API. It's actually not object-oriented. It's very function-oriented. So it has a very clean interface for creating finite element stiffness matrices and computing element forces. It's open source, so every function should be readable. I hope that there are not too much obfuscated code in it. It supports a lot of elements. If you have gone some of the other structural mechanics course, you know that. The new thing with CALFEM for Python is we are using, instead of using MATLAB for the linear algebra, we're using NumPy. Plotting is done by Matplotlib. There is also something I will go through in the next lecture is mesh generation, which is not. There are some functions in MATLAB version of Python, or MATLAB version of CALFEM, but it's significantly improved in the CALFEM Python version. So what we're going to learn here is basic workflow, how to set it up, how to use it, the differences between the CALFEM MATLAB version and the CALFEM Python version. I will also show you that there is a new manual. So we did this manual just a couple of weeks ago for another course, because now Python is the first language which you will learn in this. And that's why we, in the first, I think it was Beam Theory course, they use CALFEM for Python now. So we rewrote the complete manual that probably you have in a book form. It's available here online for Python. There is also a MATLAB version for this. And here you can find all the element functions, the theory, everything is online. So if you want to search for a function here, QE, you can find it here. And you can see how you should call it, what it returns. And when you use the CALFEM for Python, you will get NumPy arrays back. In some cases, you will also get the CALFEM matrix, but it's compatible with NumPy as well. There is also a GitHub repository. This is the code for CALFEM for Python. And an interesting folder here is the examples folder. So there is a lot of examples here that you can try out yourself to get a feel of how you should implement your problem in this course. Some of the hints are in here. So have a look there before getting stuck yourself. I think this is also a web-based version of that. Yeah. Yeah. There are more examples in GitHub. Yeah, so we have, in the CALFEM manual, we focused on the existing examples we had in the book, but reinterpreting for Python. So there are more examples in GitHub. But there are a different level of quality assurance. So, but the ones that we have in the manual should be checked and working. But yeah. The modules that builds up CALFEM is the calfem.core, which is the element routines and the system routines. And then there is a utils module as well, which contains some routines for reading and writing text files and some other things that are not kind of related to finite element. It's in the utils routine. CALFEM geometry you will use when you're starting to do the mesh generation, where you will define a geometry. And then there's a CALFEM mesh, which is the mesh generation module, where you can generate either off top chord and form your geometry. And then there is the CALFEM VS module and the CALFEM VS MPL. We are going to use the CALFEM VS MPL, so that's from Matplotlib. There is an older one called CALFEM VS, which uses another plotting library, which we are not going to use. You probably already installed it, so it's pip install CALFEM Python. Now we're going to do it here in our cloud instance here. It was done. Yeah, and this you should already know what the general procedure. You define the model, define the geometry, problem domain, material properties, boundary condition, loads. You generate element matrices. You call the element matrix routines. You assemble the global system, apply boundary conditions and solve, and then you calculate the element results. So let's start with a really simple example, a system of springs. So they are connected here on the left side and right side. There's a force in the middle. There is a spring with a 2K stiffness and a K stiffness here and a 2K there, and are connected in parallel. We have our elements here, 3, and we have 3 degrees of freedom here, 1, 2, and 3. Some properties here, force of 100 newtons in the middle. Yeah, then we import, first thing we need to do is import NumPy, of course, CALFEM core, and we do use these conventions in all examples. So import CALFEM core as CFC, import CALFEM VS MPL as CFB. then all the examples will work the same. So then we define the element topology by defining an EDOF matrix. And in this case here, please note that this is the only thing that is different in CALFEM Python with Python is that degrees of freedoms in the examples are one-based, because we want the examples to be runnable with MATLAB and with Python. So all the routines that do the assemblation use one-base notation. So here you have element 1 goes from 1 to 2, and 2 and 3 goes from 2 to 3, and 2 to 3 here. So if we run this, it looks like this. Then we define the global stiffness matrix K using mp.zeros, force mp.0, 3 by 1. It looks like this. And then we could have created our stiffness matrix or element matrices ourselves here, because they are so simple. Is Ke equals K minus K, and so on. But we will use the CALFEM version of that. So there is a CFC spring 1e, and then we give it element properties, the spring constant, and it gives you a 2 by 2 stiffness matrix. So let's run that. We have two stiffness matrices, one for the 2K spring and then one for the top. Yes. Yeah. We have two different matrices. We assemble using the CFC assemb command, which looks almost the same as the MATLAB version, except that it doesn't return anything. So you do the EDOF row, K global and KE element here. So in this case, we have to assemble 3 element matrices. You do assemb here, give it the topology, which is first row of EDOF, K, KE2, second row of EDOF, KE1, second row, third row, and KE2. So here you can also see, even if we have one-based degrees of freedom, we still have zero-based access in our arrays, because that is the notation of NumPy. And then we see here we have a final assembled stiffness matrix. Then we solve the equation system. We have to set up the boundary conditions, and we have a fixed on the right and left side. And we have to create a BC array to define our, let's see here. We have 1 and 3, they are prescribed. And the thing is with the Python version is that in MATLAB you mixed the degree of freedom and the value to prescribe in the BC. We don't do that here. If you only give a BC, it's assumed that it's prescribed to 0. You can give an additional BC val with the values you want to prescribe as well. But in this case here, we define BC array degrees of freedom 1 and 3 are prescribed. We have the middle node that has 100 here, and note again, this is the zero-based. It's a bit confusing. You have to think about when you access an array that's zero-based. Degrees of freedoms and EDOF is one-based. Remember that. And then we use solvec, similar to the MATLAB version, KFBC, and returns displacements and reaction forces. Like that. And then we want to calculate the resulting forces. We can do that with, first we have to extract the element displacement for each element, and that we can do with extract LDisp. It's a bit different from MATLAB here as well. And then we do the actual spring forces here using spring 1s. So you can see here also. Most of the functions, if you are in doubt, you can just hover over them. You can get the parameters here. And then we can print them out like this. Yeah. Then we go to bit more complex. We have a truss. We have, I think we have 8 degrees of freedom, and some material parameters here. So the first thing we're going to do is to define our EDOF. So we have 2 degrees of freedom per node, so 1, 2 to 5, 6, 5, 6 to 7, 8, 3, 4 to 5, 6, 1 based. We have an 8 by 8 global stiffness matrix and a force vector of 8 by 1. We define our material properties or variables because we have 3 different materials, A1, A2, or areas on the beam or the bars, and we define EP1, EP2, EP3, which we will use later on to create our matrix or element matrices. Now we want to create, we need to define our element coordinates. So we have EX1, EX2, EX3, EY1, 2, and 3, and we just give them our coordinates. You could have skipped the array here. You could have used lists here as well. And then we have the bar2e function that takes an element x coordinates, element y coordinates, and element properties as input. And then we create our 3 element matrices using the bar2e command. And then we assemble them in the same way we did before with the asm command. And then we get something out here. And then we solve it. Now we have prescribed variables here. Let's go back to the image here. We have xy, xy, xy prescribed here in these 3 nodes. So we define here BC equals 1, 2, 3, 4, 7, 8. We have F6 is equal to minus 80 kilonewtons. We solve it like this. And here you can see that the displacement is 0 in 1, 2, 3, 4, and 7, 8, which should be correct. And then we have a bar2s here to calculate the forces in the bars. We extract the element displacement first, and then we calculate the forces in each bar, N1, N1, N2, and 3. Finally, we have a more complex structure. You probably recognize them from other places here. So we have, let's see here, we have 12 degrees of freedom. And here we have a bit larger element EDOF. We have a 12 by 10 global stiffness matrix. We define some variables for our materials. Here we have EX and EY as arrays now. And now we are going to do it more efficiently. Now, instead of calling every time to assemble things, we should loop in Python, because that is more, if we have a large number of elements, we need to loop. We can't do it statement by statement. So the strategy is to iterate of all elements, and for each element we extract the coordinates, and then we compute the stiffness matrix using bar2e and assemble it in the global stiffness matrix. And what we're going to do is we're going to use the zip function to get all the stuff we need for each loop iteration. So in this case, we need to have the element coordinates for each element. We need to know the topology of each element. So we are going to loop over EX, EY, and EDOF. And what we assign them to ELX, ELY, and LTOPO. Those will be, for each element, the coordinates and the topology. And then we can use KE equals to bar2e, ELX, ELY, EP. So the same properties for all elements, and then assemble it using LTOPO. We did that. Then we have to define our boundary conditions. So 1 and 2 and 3 and 4 are 0. And then we assign our loads and solve the equation system. And now we are going to loop on the other side as well. So we are going to loop and extract element forces. And then we need to know, so now we do it on a global level here. So we call LDISP EDOF A, and then we get an E element displacement array with the displacement for each element on each row. And then we also need somewhere to store our element forces. So we create an N here, which is the same size as the EDOF shape 0. So the number of rows is the same. We just do an array of the forces. And then we need a loop variable for our N as well here, so we can access it. And then we do the same thing, ELX, ELY, ELD now for the forces, and then we zip over EX, EY, ED. So then each iteration we will get the element coordinates and the displacement for each element. And then we call bar2s, ELX, ELY, EP, ELD. We assign NI equals to ES0 item. And this is because some of the functions here return arrays. So we need to extract the scalar from a 1-by-1 array. So you can do that by calling the .item method of an array. Not ideal. This is something we will work for in the next version of CALFEM as well. And then you get all the forces here out. I think I will, let's see if I can do this as well. It's a bit more complicated here. This is a mixed beam and bar system. So when you have both beams and bars or different element types, you will have a different number of degrees of freedoms here as well. So if we can zoom in a bit here, you will have 3 degrees of freedom here on the top for the beam that goes here. Then we have 2 bars here that connect to the 2 degrees of freedom here, and we have 2 degrees of freedom here. So what we do here is that we have a chord array, and we have a DOF array for the 3 degrees of freedom nodes, and a second one for the 2 degrees of freedom nodes. And then we have different EPs here. So we have EP1, EP2, and we have EDOF1. So these are the beam elements that goes from 1, 2, 3 to 4, 5, 6, and so on. And we have the EDOF2, that is the bar element, goes from 13, 14 to 4, 5, and so on. They are only assembling to those degrees of freedom. We calculate using chord extract here, EX and EY from EDOF chord DOF. So this is a method that can be useful if you don't want to do the EX, EY yourself. You can give it an EDOF, a coordinate, and a DOF array, and it will extract element coordinates for you. And then we have 2 loops now. We have to assemble the beams, and we have to assemble the bars. So we do first, like before, with the zip, EX1, EXY, EDOF1, and then we do the beam loop, beam assembly. Did I miss something here? Okay, I will assume it works then. I have to check why that doesn't work. And not enough we don't pack expected 3 got 2. Okay, I will check what that error is. But then you loop it twice. And here you have BC prescribed again. And you put that in the array, and then you solve it. And then you have to do 2 different extraction loops here as well. But I hope that you get kind of the idea. It's not very different from normal CALFEM. The only difference is that you have the 1 based for the degrees of freedom. If you have EDOF going into ASM, for example, it assumes it's 1 based. If you have, but if you access the arrays, you have to access them 0 based.